Good morning. I'm Dr. Niti Maheshwari, Assistant Professor, Ajay Kumar Garg Engineering College, Department of Applied Sciences. Today, I'm going to deliver a lecture on UV visible spectroscopy. Now, this topic, it is covered in Module 2 of Engineering Chemistry, whose subject code is CAS 102T/202T. Now, coming to the topic, what do we understand by the term spectroscopy? Now, this term spectroscopy, it is a branch of science which deals with the interaction of electromagnetic radiations with matter. Since the electromagnetic radiation starting from the gamma rays to the radio waves, their frequency or we can say their wavelength is different. Therefore, their interaction with the matter is also different. Now, coming to the topic, which is UV visible spectroscopy. What is the principle behind the UV visible spectroscopy? UV visible spectroscopy deals with the transitions in the range of 200 to 800 nanometers. This is the range where the light is absorbed by the matter and different transitions are seen. Now, in this case, the UV visible spectroscopy, it involves the absorption of UV visible light by a particular molecule, causing the promotion of an electron from the ground state to the excited state. What do we mean by this statement is a molecule, it contains three types of electrons. It contains three types of electrons. N, pi and sigma. This is a sigma bond, this is a pi bond, and if there is an atom containing lone pair of electrons, now these electrons are non-bonding electrons, which are N electrons. So, three types of electrons are present in a molecule, the sigma, pi and the N electrons. So, this spectroscopy involves the transition of these three types of electrons from the ground state to the excited state. The region of the ultraviolet visible spectroscopy is from 200 nanometers to 800 nanometers, 200 to 400 nanometers for the UV range and 400 to 800 nanometers for the visible range. The common solvent which we are going to use for the preparation of the sample which is to be analyzed is either ethyl alcohol or cyclohexane. Why these two are used? Because in ethyl alcohol, as you can see, all the bonds, they are saturated. All bonds are saturated and it contains only non-bonding electrons. So, since the bond near these non-bonding electrons is a sigma bond, it is going to show either the sigma to sigma star transition or the N to sigma star, that is a high energy process transitions are going to be seen. So, generally these transitions, they are not seen in this spectroscopy. Hence, this ethyl alcohol is transparent in the entire region of 200 to 800 nanometer. Similarly, for cyclohexane, this is the structure for the cyclohexane, as again you can see all the bonds are saturated. So, again the cyclohexane is going to be transparent in the entire 200 to 800 nanometers. Therefore, we can use these two as the common solvent for dissolving the samples. Next, coming to the type of electronic transitions, as I have already said that there are three types of electrons which are involved. Therefore, the electronic transitions will also depend on these three types of electrons. The different transitions which we can see, here you can see there is a sigma electron, pi electron and non-bonding electrons. Since the sigma bond is the most stable bond, so this energy of this sigma electrons is going to be minimum. Hence, which means that you require a higher amount of energy to excite these electrons from ground state to the excited state. The next energy, a little bit high energy, it is occupied by the pi electrons, and the non-bonding electrons, which are free electrons or lone pair of electrons, their energy is maximum. So the different types of transitions which we can see in the UV visible spectroscopy are either sigma to sigma star transition, or the movement or the transition of lone pair of electrons to the sigma star, that is N to sigma star transition, or pi to pi star transition, the movement of the pi electrons to their pi and pi star antibonding, and N to pi star transitions. So these are the 4 different types of transitions which are seen in the UV visible spectroscopy. Next, coming to the order of increasing energy. Since sigma bonds, as I've already said, are the stable or the most strongest bonds, therefore the transition of sigma electrons from ground state to the excited state, it requires maximum amount of energy. Next, energy is required by the lone pair of electron, that is N to sigma star transitions. Now in this case, since there is a lone pair of electrons, but for these them to show the transition, the nearby bonds are sigma bonds. So such type of molecules, they show N to sigma star transitions also. Next is pi to pi star transitions, and least energy is required for N to pi star transitions. So the possible electronic transitions, they are sigma to sigma star transition, pi to pi star transition, N to sigma star transition, and N to pi star transition. The fourth one is the N to pi star transition. Coming first to the sigma to sigma star transition. Now, these transitions, they are generally shown by the saturated hydrocarbons, and these transitions, they occur by the sigma electron or the transition of sigma electron from its bonding orbital to the excited anti-bonding sigma star orbital. As you can see, this is the sigma bonding and this is the sigma star which is anti-bonding. This is also going to be clear by the MOT, molecular orbital theory, and the transition of electrons from the lower ground state level to the excited state level. Now these transitions, they require very high energy and they get absorbed at the lower wavelength. For example, you have methane, ethane, propane and the whole series which are going to show such type of transition. And the UV visible range that we are covering, it is from 200 to 800 nanometer. And for sigma to sigma star transitions, generally we require a region below 200 nanometers because they require very high energy, so they occur at shorter wavelengths. Now, on moving below 200 nanometers, what happens? Up to 180 nanometers, we can see the transitions, but just as we move a little below 180 nanometer, the oxygen, it starts absorbing, and hence to study these transitions, the entire path length has to be evacuated. So in the normal UV visible spectroscopy, the sigma to sigma star transitions are generally not seen. They do not appear in the normal UV visible spectroscopy. Next is pi to pi star transition. Now, this type of transition is generally seen in those compounds which contain a pi electron, a pi bond. And these transitions, they are associated with normally those compounds which contain a double bond or a triple bond. And these transitions, because the pi orbital already is at a elevated energy state, so these electrons do not require a higher energy as comparison to the sigma electrons for their transition. So the pi to pi star transition require lesser energy in comparison to sigma to sigma star or n to sigma star transition. And the compounds, as you can see, the alkenes or the alkynes or the carbonyls, alkenes, C double bond C containing compounds, C triple bond C containing compounds, nitriles, aromatic compounds like benzene, they all show pi to pi star transitions. Next is N to sigma star transitions. Now, these transitions, they are generally seen in the saturated compounds. Saturated compounds containing a heteroatom or any atom which has a lone pair of electrons. Generally, it is the heteroatom. So, here you can see compounds which contain either oxygen, nitrogen or sulfur or the halogens. But they are saturated compound. That means all the bonds are saturated or single bonded. They are capable of showing N to sigma star transitions. And these transitions, they require lesser energy in comparison to sigma to sigma star transitions, but more energy than the pi to pi star transitions. So here the example, this is C2H5. If we excite or if we keep this molecule in the UV visible spectroscopy, we put the radiations, then these electrons are going to get excited and they are going to utilize the sigma star orbital of either one of these. So this type of transition is N to sigma star transition. Similarly, methyl chloride. Now here chlorine has a lone pair of electrons. Again, since all the nearby bonds are saturated, therefore the electron are going to show the N to sigma star transition. There is no pi orbital available to them. In case of ketone also, let's see the case of ketone. Now in the case of ketone, one bond is sigma bond and the other one is the pi bond. And this oxygen, it contains two lone pair of electrons. Now here you can see these lone pair of electrons, they can either utilize the pi orbital or they can utilize the sigma orbital, pi star or the sigma star. If these non-bonded electrons, they utilize the sigma star orbital of the bond, then they are going to show N to sigma star transition. Last type of transition is N to pi star transition. Now, N to pi star transitions is generally shown in those compounds which contains unsaturation. That is, double or triple bond is already present, and along with the double or triple bond in the compound, they also contain the heteroatoms. Heteroatom, those atoms which contain lone pair of electrons, and the electron from the non-bonding orbital is promoted to the anti-bonding pi star orbital. And so compounds which contain double bond having heteroatoms, such compounds are carbonyl compound or the nitriles or the nitro compounds. Such compounds, they show such type of transitions. As I have already discussed the case of CO. In CO, one is the sigma bond and the other one is the pi bond. And these are the lone pair of electrons or the non-bonding electrons. If the non-bonding electrons utilize the pi star orbital of this pi bond for its transition, because this type of transition require least energy, there are chances, maximum chances that the non-bonding electrons will get promoted to the pi star orbital of the CO bond. It can again show N to sigma star and N to pi star. So, lower energy, at lower energy, it is going to show only N to pi star. But if we increase the energy of the radiation, if we increase the frequency of the radiation, then it will show N2 pi star as well as N2 sigma star transitions. Both the transitions can be seen. Now, these N2 pi star transitions, they require minimum energy and they show at the longer wavelength around 300 nanometer. Now, in UV visible spectroscopy, there are different terms which are used. Coming to the first term, very commonly used in the UV visible spectroscopy is the chromophore. Chromophores are nothing but the part of the molecule which is responsible for giving color to the molecule. It is called as the chromophore. For example, if the molecule contains nitro group, this nitro group imparts yellow color to the compound. So, chromophores are nothing but the covalently bonded unsaturated group which are responsible for electronic absorptions. And the chromophores, they show absorption either due to N2 pi star or pi to pi star transitions or both. So, chromophores are nothing but the part of the compound which is responsible for imparting color to that specific compound. So, such group is known as chromophores. For example, nitro group, NO group, CO, CN, C triple bond N, C double bond C, C double bond S. Now, here you can see that all the groups, they contain double or the triple bond, that is unsaturation is present. Along with that, there is a heteroatom. Heteroatom which contains lone pair of electrons. So, there are heteroatoms which are going to contain lone pair of electrons. So, you can see that one bond is going to be sigma, the other is pi, similarly one sigma and 2 pi, and the nearby bond is a heteroatom which contains lone pair of electrons. So, these lone pair of electrons, they are going to show N2 pi star transitions, and this pi bonding which is present between the atoms, this is going to show pi to pi star transitions. And as you have seen earlier that the N2 pi star and pi to pi star transitions, they require least energy, minimum energy. Therefore, they generally show absorption in the visible range. And if the absorption is seen in the visible range, then according to their absorption, they are going to impart color to the compound, because in the UV, the light is white, but you show different colors only in the visible range, that is from 400 to 800 nanometers. So, these absorptions generally occur at longer wavelengths. Only then such groups, they impart color to the compound. Now, next, that was the case when there is single double bond and there are lone pair of electrons. But when double bonds, they are present in conjugation, then the lambda max is shifted to a longer wavelength. I am going to discuss this later, how the lambda max shifts towards the longer wavelength. But here you can see there are two double bonds in 1,5-hexadiene, but there is gap in between. These double bonds, they are not present in conjugation, and you can see that their lambda max is at 178 nanometers. That means it is at shorter wavelength or the higher frequency. But if these bonds are in conjugation, that means alternate double and single bonds are present. As in the case we are seeing in 2,4-hexadiene, the value of the lambda max, it shifts towards the longer wavelength. Only by changing the position of the double bonds, the absorption maximum, lambda max of the two compounds is changing. For unconjugated systems, it is at higher frequency. or the shorter wavelength, and for conjugated system it becomes or it comes at the longer wavelength. I am going to discuss this later how it is happening. Next common term which we use in the UV visible spectroscopy is the auxochrome. Now, what we understand by the term auxochrome? Now, auxochrome is nothing but the color enhancing group. For example, auxochrome works in addition to the chromophores. Chromophores are color imparting groups. That means if the chromophore is not present in the molecule is not going to show the color. But in addition to the chromophore, if auxochrome gets associated with the chromophore, then it increases the intensity as well as the wavelength of the absorption maxima. Now here I am going to show you one example. This molecule is benzene, and here you can see that there are alternate double and single bond. That means benzene is working as a chromophore because it is showing pi to pi star transition, and since the molecule contains conjugated systems, therefore the value of lambda max will be higher. If I attach a group OH to the benzene, that is phenol, now it becomes phenol. Now the electrons which are present on the oxygen, they are going to get involved in conjugation, or I can say that this phenol group is going to increase the conjugation of the benzene. So auxochromes are nothing but those groups which have the ability to involve their electrons in the molecule, and they are going to increase the number of conjugated systems in the molecule. And once the auxochrome does that, it increases or changes the intensity as well as the wavelength of the absorption maxima. As the more number of systems, double bonds, come in conjugation, as the level of conjugation increases, the value of lambda max also increases. Generally, the auxochromes are the saturated groups, as chromophores are those groups which contain pi orbitals. So they are unsaturated, but the auxochromes, they are saturated groups. And certain examples are the amine groups, or the OH, or the OR, or the amides, or the SH, etc. Different groups, on attaching to the chromophores, they are able to vary the absorption maxima of the compounds. Now here you can see benzene, it is acting as a chromophore. I have already discussed. Here are the double bonds, and it is showing lambda max at 255 nanometer. Now in the case of phenol, if I am attaching OH group to the benzene, now the oxygen electrons which are present, non-bonded electrons which are present on the oxygen, they are going to get involved into the conjugated system. So the value of lambda max, it increases from 255 to 270 nanometer. And in case of aniline, the value of lambda max further increases. Again, nitrogen is capable of involving its electron in the conjugation. The lambda max also increases from 270 to 280 nanometer. Reason being, since nitrogen is less electronegative than oxygen, so it is going to release its electron easily in comparison to the oxygen. Lesser is the electronegativity, lower is the binding property of the free electron with the electronegative atom. So electron easily will favor its nitrogen will easily favor its electron to the conjugated system. It is going to extend the conjugation more easily in comparison to the phenol. Sorry. Next, coming to the absorption and intensity shifts, the lambda max shifting. Now, 4 different types of shifts are there. Bathochromic shift, which is also known as the red shift, hypsochromic shift, which is also known as the blue shift, hyperchromic effect and the hypochromic effect. 4 different types of shifts are there. Now, here I am showing you a diagram between absorbance and wavelength, and this diagram, it is showing a position of the lambda max. Now, what exactly is lambda max? For any element or any compound that I want to study, I am going to study it in the entire UV visible range from 200 to 800 nanometer, and the position at which I am going to observe the maximum absorbance, that position is going to become, that wavelength is going to become my lambda max. It is not that every substance will show the absorbance, constant absorbance in the entire range. No. At 200 nanometer, some other absorbance is going to be seen, 250 something else, 300, 350, 400, this absorbance is going to vary. So, in the range from 200 to 800 nanometer, at which point the substance is showing maximum absorbance, that point is the value of lambda max. That is the wavelength maxima. And if by certain effect I am able to shift this lambda maxima towards the right side, that is towards the longer wavelength side, then it is known as the bathochromic shift or the red shift. And by some effect, if I am able to shift the position of the lambda max, or it shifts by certain effect to the shorter wavelength or the higher frequency side, then it is the blue shift or the hypsochromic shift. And the effect by which the position of this lambda max increases or the absorbance increases, it is known as the hyperchromic shift, and the effect by which the position of the absorbance decreases, it is known as the hypochromic shift. I am going to take these one by one. Coming first to the bathochromic shift. So, when the absorption maxima of any compound, it is going to shift at the longer wavelength, then it is known as the bathochromic or the red shift. Now, this effect is generally seen by the presence of either an oxochrome or by the change in solvent. One example I am going to take here. Now, this is a polar bond. So, positive and negative charges, delta positive and delta negative charges are there, and these lone pair of electrons are present. If I keep this, keep this compound in the polar solvent, now the polar solvent will also have delta negative and delta positive charges. It is going to have negative and the positive ends. So, the delta negative and delta positive is going to be present in the polar solvent. These non-bonded electrons, they are going to get attracted towards the delta positive charge, or you can say they are going to show attraction, or they are going to get binded by the electrostatic forces of attraction. But if I reduce the polarity of the solvent, if I am going to reduce the polarity of the solvent, then these attractive forces are going to become weak. So, first, before, when the solvent was polar, these non-bonding electrons were binded by the solvent. So, on excitation, for the excitation of these non-bonded electrons, we would require higher energy. But on breaking the electrostatic forces of attraction between non-bonded electrons and the polar solvent, that is by reducing the polarity of the solvent, these non-bonded electrons, they are going to become free. And when they are going to become free, then their N to pi star transition, the energy required for this N to pi star transition is going to decrease. And when this energy decreases, N to pi star transition energy decreases, That means the wavelength is going to increase. So, by reducing the polarity of the solvent, N to pi star transition is going to show the bathochromic or the red shift. Other examples on introduction of an oxochrome like OH, OCH3, they causes absorption of compound at the longer wavelength. Second type is the hypsochromic shift or the blue shift. Now, when the position of the absorption maxima, it shifts towards the lower wavelength side, then it is known as the blue shift or the hypsochromic shift. And this may happen because of the either by removal of the conjugation or by the change of medium. Again, that example that I had taken of CO, if I am going to change from non-polar to polar solvent, then the N to pi star transition is going to show the blue shift instead of the red shift. By removal of conjugation also, for example, in aniline, the non-bonded electrons which are present on aniline, they are involved in conjugation, but on keeping this aniline in acidic solvent, I am going to form anilinium ion. Now, here you can see that there are no lone pair of electrons available to be included in the conjugation. Hence, instead of increasing the conjugation, I am decreasing the conjugation. So, on decreasing the conjugation or by the removal of the conjugation, the shift that is going to be observed is the blue shift or the hypsochromic shift. Next is the hyperchromic effect. Now, by this effect, the intensity of the absorption maxima it is going to increase. As I have already discussed that the chromophores are the compound which impart color. But if we add oxochrome to the chromophore, then the intensity of the color increases. That means it is going to have a new value of the absorption maxima. So, when the intensity will increase, the absorption maxima will also increase and it will give rise to the hyperchromic effect. So, this is usually seen by the introduction of an oxochrome. Last is the hypochromic effect. So, by this effect, there is a decrease in the intensity of absorption maxima, and generally it is seen by the addition of those groups which distorts the geometry of the molecule. If any group is included which is going to distort the geometry, then by distortion of the geometry, a hypochromic effect or the reduction in the absorption maxima is seen. For example, this molecule is biphenyl and this molecule is highly symmetrical. You can see it is highly symmetrical. But on addition of a methyl group, I am distorting the geometry. So, here on distortion of the geometry, the 2-methyl biphenyl is, in case of 2-methyl biphenyl, the absorption maxima is going to decrease. Coming to the applications. Now, these UV visible spectroscopy, it can be used for the characterization of aromatic compounds or the conjugated olefins. We can use it for the detection of impurities or for the isomers. Then this can also be used for the determination of molecular weight using Beer's-Lambert's law. Again, study of kinetics of chemical reactions can be done, and it can also be utilized for the quantitative analysis of pharmaceutical substances and drugs. Next, now why the conjugated systems have higher value of lambda max? Now here you can see that there are 2 double bonds. These are one pi bond, another pi bond. Now these two, when two pi bonds they are in conjugation, they combine by two types. Either they can combine in phase or they can combine out of phase. If they are going to combine, when pi is going to combine with pi, then it is going to form psi 1, and you can see there is no node is going to be present here. They are all in phase. If they combine out of phase, that is pi minus pi, then they are going to form psi 2. Here that means that pi minus pi, there is one double bond, but there is a node in between. So when they combine out of phase, one node is going to be present in the psi 2. In psi 3, in the pi star orbital, if they are going to combine, when pi star is going to combine with pi star, addition effect, then it is going to be known as psi 3. And if pi star is combining out of phase with pi star, then it is known as psi 4. Here two nodes are present, and here you can see there are out of phase combination, therefore three nodes are going to be present. When there is single double bond, in case of single double bond, the transition occurs from psi 1 to psi 3. But in case of psi 1 to psi 4, but in case of conjugated systems, this is the highest occupied molecular orbital psi 2, and this is the lowest unoccupied molecular orbital, which is psi 3. That means the value of highest occupied molecular orbital, it is going to be raised, and the value of energy level of lowest unoccupied molecular orbital is going to decrease. So the transition is going to take place from psi 2 to psi 3. As you can see, the energy required from the transition between psi 2 to psi 3 has reduced considerably. Therefore, when the conjugated systems are present, they usually occur at, when the energy is going to decrease, the wavelength is going to increase. It is going to occur at longer wavelength. That was the case in 1,3-hexadiene and 2,4-hexadiene. Why 2,4-hexadiene? It shows absorption at the higher value of lambda max. Next, what is the effect of polar solvents of N2 pi star and pi 2 pi star transitions? Now here you can see N2 pi star I have already discussed. This is the N electrons and this is the pi electrons. So N2 pi star transition, if we have polar solvent, as I have already discussed, it is going to have positive and the negative ends. So N electrons will bind by the sigma delta positive charge. So for the excitation of these bonded lone pair of electrons, we are going to require higher energy, as when the polar solvent was not present. When they were free, they are going to require lower energy, but in the presence of polar solvent, the energy required for excitation of lone pair of electrons is going to increase. So the N2 pi star transition will show blue shift when the solvent is polar. And let's see what effect it has on pi to pi star transition. This is the pi bond. This is delta positive and delta negative. If we have the polar solvent, it is going to get attracted towards delta negative and oxygen will get attracted towards the delta positive. So here you can see this pi bond is going to undergo stretching. Since the oxygen is getting attracted towards the delta positive of the polar solvent and carbon is getting attracted towards the delta negative of the polar solvent, the extension of the bond will take place. So when the bond is going to get expanded, here you can see the stability of bond is going to decrease, and when the stability decreases, the energy automatically gets elevated. When it was stable, it was at this energy level, and for transition pi to pi star transition, suppose we required this energy, but when it is in a stretched condition, now the energy of the pi orbital has already increased. So for pi to pi star transition, it will now require only this much energy. Hence, the pi to pi star transition in the presence of polar solvent is going to show redshift. It will occur at a lower wavelength, whereas N to pi star will occur at a longer wavelength. Thank you.